Hello and welcome to Kernel of Knowledge. In this video we're going to cover network protocols. Now you may have heard of network protocols but maybe you're not that familiar with them. Well, by the end of this video you'll know everything you need to know for system design interviews about network protocols. Let's start with what exactly is a network protocol. When you have a client and a server, they need to communicate. And how do they know what to communicate? What if one speaks English and the other speaks Chinese? They're never going to be able to communicate correctly. And that's where network protocols come in. They are an agreed upon set of rules and conventions that allow clients and servers to communicate in a consistent way that both understand. You can think about protocols similar to when you introduce yourself to someone new. The general protocol is that you introduce yourself, you say your name, you shake their hand. That's a protocol between two people. Clients and servers have the same sort of thing. And there are a number of protocols, and we're going to cover the main ones in this video. So we're going to cover IP, or the Internet Protocol. We're also going to cover TCP, the Transmission Control Protocol. We're going to cover UDP, or the User Datagram Protocol. And we'll also cover HTTP, or the Hypertext Transfer Protocol. The communication between two machines is done via the network protocol then. And that defines the type, the format, the order, the expected response, and everything that's required for those two machines to communicate across the internet. The first protocol we're going to take a look at is the Internet Protocol, or IP. Unsurprisingly, this is what the internet itself is built upon. And it's also where IP address comes from, the Internet Protocol address. Now, you can go really in depth into IP, TCP, UDP, etc. But for most system design interviews, you don't need to. You just need to have a high level understanding and maybe a little bit more depth than some candidates. Ultimately, when two machines communicate across the internet, it's done via IP packets. You can think of these as envelopes of bits of data that are being sent across the internet from one computer to another. Ultimately, we are, of course, sending binary between the two machines. The binary data, of course, needs to conform to the specific protocol, and in this case, it's going to be the Internet Protocol. IP packets themselves are built of two things. You have the header and the data. Now, the header itself has a lot of information about the packet itself, such as the source and destination address, the ID of the packet itself, and some ordering via the fragment offset. You can see here that there's lots and lots of data contained within the header, and this is all used by the protocol. It's important to note that there are currently two versions of the Internet Protocol. You have IP4, which is what we're using in this example, and you have the newer IP6. The max size of a packet is 64 kilobytes in IP4, and it's probably pretty obvious you can't really fit all your data into just 64 kilobytes. So we end up splitting the data up into multiple packets and sending those packets across the internet. However, what happens when a packet fails to get sent? What happens when there's an error in between the communication? Well, the Internet Protocol simply can't handle this in a good way. And that's where TCP, or the Transmission Control Protocol, came in to help solve the problems that IP has. TCP, or the Transmission Control Protocol, adds several critical capabilities on top of IP, or the Internet Protocol. Some of these are reliable delivery. So TCP ensures that all data arrives at its destination through acknowledgements and retransmission of lost packets, as we'll see in a bit. It also offers ordered delivery. So TCP assigns sequence numbers to guarantee data is delivered in the same order it's sent. TCP also has connection management, stream-oriented data transfer. This means that TCP treats data as a continuous stream rather than discrete packets like IP. It also adds error detection and the ability to handle port numbers. So with TCP, you can add a source and destination port to differentiate multiple connections at the same host. IP alone simply handles routing of packets from source to destination with no guarantees about reliability, ordering, or connection state. TCP ultimately builds these crucial guarantees that are required for internet communication on top of IP's basic packet delivery system, making it suitable for applications that require reliable communication. TCP ultimately allows us to send lots of data in a reliable way. We could go really deep into TCP, but for system design, we don't really need to. We just need to know that TCP builds upon IP. And as we can see, TCP packets also have a header and data, and they are passed within the IP packet themselves. When we use the TCP protocol to communicate, the protocol first does what's known as a three-way handshake to establish the connection between the client and server. As you can see here, we first have the SYN or the synchronization request. We then have the SYN ACK or the synchronization acknowledgement response. The client then sends back the acknowledgement. And at this point, the client and server are communicating with each other via TCP. They've established the handshake and they've opened up the connection to send the data across. Let's take a look at an example of a failing packet in TCP. In this example, we're going to send the word cat. So in the first packet, or packet 1, the client sends the letter C across to the server. The server acknowledges that it's received packet number 1, and because TCP packets are ordered, it knows it's the first packet. It sends the acknowledgement back that it's received packet 1. Packet 2, the letter A, gets sent from the client to the server, but the server never receives it for some reason. And because the packets are ordered, the server knows that it should be receiving packet number 2, second in the sequence. Packet 3, letter T, then gets sent from the client to server. And because the server is still expecting to receive sequence number 2, it's going to hold packet 3. And it will acknowledge that it's got packet 1, and it's at the first of the sequence. It's then going to time out at this point, and the server is still waiting for packet 2. The client is then going to know that because it's got back an ACK 1, it needs to send packet 2 again, at which point it's going to send packet 2 to the server. The server is going to acknowledge that, and it's going to acknowledge it with sequence number 3. And it's going to acknowledge it with sequence number 3 because it's already got packet 3. It's been holding that packet. And at this point, we've got all 3 packets, and the server has managed to order them correctly and respond correctly. So this is just an example of a failing packet and the client having to resend it via TCP. Much like TCP, UDP, or the User Datagram Protocol, provides a set of features on top of IP. Now, UDP is much more lightweight than TCP, but it offers port numbers. Like TCP, UDP adds the source and destination port numbers to allow multiple applications on the same host to use the same network simultaneously. It also adds in a checksum. So UDP includes an optional checksum for some basic error detection, although it's nowhere near as robust as TCP's. It also adds in multiplexing, which is the combination of IP addresses and port numbers allows for communication between specific applications. And it's also datagram oriented. So unlike TCP, which treats data as a continuous stream of bytes, UDP strictly preserves message boundaries. And this has a few implications. So firstly, in terms of message integrity, when UDP sends a datagram, the exact datagram, if it arrives at all, will be delivered to the application as a single discrete unit. The receiving application gets either the complete message or nothing at all. With UDP, there's no reassembling or reordering. If a packet is lost, it's just lost. It's send and forget. So the client transmits the datagram and it doesn't track or wait for an acknowledgement. It just sends it over. And there's no built-in way for it to know if it's been received or for the server to recover it. This basically pushes all the responsibility onto the application. UDP is very efficient for small messages, and it does have some size constraints, but ultimately UDP is a very useful protocol, and you'll find it's used for applications where speed is more important than reliability. So things like real-time media streaming, gaming, VoIP, those kind of things, where speed is more important than the reliability and the recoverability. So to compare TCP versus UDP, in terms of the connection, TCP requires the handshake, as we've seen, whereas in UDP it's connectionless. There's no handshake at all. In terms of reliability, TCP guarantees the delivery, whereas UDP offers no guarantee. In terms of ordering, TCP has ordering packets, whereas in UDP there is no packet ordering. TCP is slower due to the overhead of the connection and the ordering, whereas UDP is much quicker due to the simplicity of the protocol. TCP has flow control, whereas UDP doesn't. TCP can handle errors in an extensive way, whereas UDP is just basic error handling. And in terms of the header size, TCP is 20 to 60 bytes, whereas UDP is just 8 bytes. And as I said, in terms of use cases, UDP is for things that are much more performance-based, so like gaming or video streaming, whereas TCP is used for things like web browsing, email, or file transfer. You now know a little bit more about the network protocols, and you can see how they build upon each other. Ultimately, the IP layer is the foundation of the internet, and TCP and UDP are both built upon the IP layer, and they're known as the application transport layer. Above those network protocols, we then have things like HTTP and, of course, things like HTML, CSS that are all used within the HTTP protocol. And that ultimately all defines the web itself. Let's now take a quick look at HTTP, or the Hypertext Transfer Protocol. And ultimately, as we know, it's a communication between a client and server, and generally the web uses HTTP. So when you go to youtube.com, you're making a HTTP request. Ultimately, it's a request and response cycle, as we know from the client server video. In terms of a HTTP request, generally you have the method, so either get or post. The path, in this case, it's just a /, this will be home, but it could be /videos or /comments. And then you have the protocol version. In this case, we're using 1.1. Within a HTTP request, you're also going to have the headers section. And this is kind of the most important section. This is the key value pairing of various bits of data. So you can see here, we've got the host, we've got the accepted language. You'll also have bits of data like the content type, which specifies what the body of the request will look like. There's also methods like post and put, etc. And they all obviously conform to the same protocol. If you take a look at the response, you can see again, you've got the protocol version. You've then got a status code, which hopefully you're fairly familiar with. In this case, it's 200, which means success. In general, you can use status codes however you want, but there are best practices and guidelines around that, which I would recommend that you stick to. You then have the status message. In this case, it's okay, but if it was a 404 status, it would say status of not found. In the response, you then have the header as well, which has more data. For example, we've got dates here, we've got cache control, and we've got the content type, which in this case is text HTML. And then you'll obviously have the body of the request as well. In this case, it would be a HTML page. So the HTML for the videos page on YouTube. HTTP itself is pretty simple. Again, you can really dive into it in a lot of detail, but the important thing to know is the status codes, the protocol version, and then the headers and the kind of data that you're wanting to send. Let's just take a look at a super quick example using a Node.js server. So on the left-hand side here, I've got a simple Node server using Express.js. You can see I've just got two simple endpoints. I've got a get/example, and I have a post/example as well. Within those, I'm just doing some simple logging of the headers, the method, the HTTP version, and then the headers, method, and the body itself. I'm going to go ahead and start this particular server, and you'll see the server is now listening on port 8080. In the terminal below here, I'm just going to go ahead and use curl, and I'm going to go ahead and make a GET request to our server. So it's going to be local host on port 8080, and it's going to be using /example. And you'll see here in the bottom, I get the response of get the example received, which is what the server is sending back. And if we look at the top here, we can see the logs. So we can see the headers, we've got the host, so localhost 8080, which is what we'd expect. The user agent, which in this case is going to be curl, because that's what we've been using, but it normally would be something like Chrome or Mozilla. And then we've just got an accept header as well, which is just accept everything basically. We've then got our method, which is get, and we've got the HTTP version. So as you can see there, On the request, we get the headers, we get the method, we get the version, and various other things. Let's go ahead now and do a post request to our server. So again, curl, this time I'm going to pass in the header flag, and I'm going to pass in the content type header, which we saw earlier in our example. And this time I'm going to use application/JSON, as I'm not returning any HTML here. This is just a basic JSON API. I'm then going to pass in the actual host itself. So localhost 8080. Again, it's going to be /example. And then data we're going to send in, this time it's going to be some JSON. So let's go ahead and do that. Let's just do hello world. And assuming I've typed that correctly, we should work. There we go. So again, we can see that we get the post example received from the response from the server. And then if we look at the logs here, again, we will see the headers. We've got the host, we've got the user agent, we've got accept, and then we've got some new headers. This time we've got the content type of application JSON, which is what we sent. And then we've got the content length, which will be the length of the JSON itself. And of course the method is post and the body is hello world as we sent. So that's just a super quick example of some headers and body and that kind of thing that you get with the HTTP protocol. Hopefully you now understand network protocols a bit better than before this video. We've covered IP, TCP, UDP, and HTTP. Ultimately, IP, TCP, and UDP are quite low level, and I'll probably do separate videos on each of those. So if you want to see that, leave a comment in the comments below. Most of the applications you build in system design will be using HTTP, and ultimately that's where all your kind of business logic is going to live within those servers that you build. Within those routes, you're going to handle all the business logic themselves. Thanks for watching. Hopefully you found this helpful. If you have, please click subscribe or the like button, as it really helps out the channel.